Hello students, welcome to today's lecture. So today we are going to discuss the centrifugal settling processes. Earlier we discussed gravity settling processes where the gravity was used to separate the particles, right, from the liquid or gas. In this case, in centrifugal settling processes, we separate the particles, right, based on centrifugal force. Okay. So how centrifugal force is generated? So if the equipment is rotating with high angular velocity, then the centrifugal force will act radially outwards. So the particle is separated based on the density in the radial direction. Okay, so the most common example is the cyclone. Okay, so we have we can separate the solids from gases using cyclones. Okay, so what is the principle behind the cyclone? So you have a this kind of the equipment, right? The this part is cylindrical, and then we have a conical part at the bottom. Okay, and at the top we have a inlet for the dust and gas mixture. Okay, so the inlet is such that it is tangential in nature. Okay, so the if you see the top view, let's say I see the top view, don't think that the inlet is like this. Gas is not coming like this. Okay, so gas is coming in at a tangential velocity. So inlet is something like this. So gas will come at tangential velocity, so it will go like this and it will rotate. Okay, so the inlet is in tangential direction. Okay, and we have a gas outlet at the top. Okay, so how it works? So gas, this dust and gas mixture will come in, right? So it will start rotating. So point is how this centrifugal force is created. So you have to increase or decrease the this flow rate or the pressure drop. So based on the pressure drop or the flow rate, the centrifugal force will be increase or decrease. Okay. So if this gas will come at very high speed, what happens? So it will have more centrifugal force. Okay. So this feed will have a mixture of small particles to large particles, right? So the larger particles, what will have is, because of the centrifugal force, they will be at the wall, right? So they will move at the wall because they have very large mass, right, compared to the small particles. So they will simply will be at the wall, and they will slide and will get collected at the bottom. Okay, but these small particles are sometimes they are carried away by the gas. Okay, so you have to check out, so you have to check the average size of the mixture. Also you have to check the particle distribution in the feed. Okay, then only you can predict the separation, how much particles will be separated at the bottom, right? So for larger particles, definitely the particles will settle out at the bottom, but for small particles it will be carried out with the gas. Okay, so then you can use some back filter here. Okay, we'll see that in gas cleaning. Okay, so this is how cyclone work. Okay, so mainly we have air here, so it is cyclone. If instead of air we use water, then it is called hydrocyclone. So that is the next part. So first focus on this cyclone. Okay, so you can see the diagram. Okay, so I have almost explained the principle. So if this particle is moving in a tangential, so it will rotate. Okay, in spiral motion. Okay, then it will come out from through the center. Okay, but the particles with heavy particles will settle at the bottom. Because they are heavy, they will experience larger centrifugal force, so the particles will always be tend to be at the wall, and they will simply slide down and they will be collected at the bottom. Okay, this is the principle. Okay, now you should know the separation factor. So what is separation factor? So this, the force because of centrifugal, yeah, force due to the centrifugal and force due to the gravity, right? This ratio Fc by Fg is defined as the separation factor. Now, based on this, you can see how easily it is to separate the particles. So, what is the centrifugal force given by? So it is nothing but mv square by r, right? So what is r? R is nothing but this radius of the cyclone. Okay. So mu square. Then what is the v? V is nothing but the tangential velocity. Okay, the inlet velocity of the air and dust particle mixture. Okay, that is the tangential velocity. So, and gc is nothing but a constant. It is 1 in SI units. And what is the force due to gravity? Mg. Ignore gc. Okay, so the resultant is u square tangential velocity square by rg. What is r? Radius of this cyclone. Okay, so let's say that a cyclone of 1 feet. Okay, 1 feet means in diameter. So in SI unit it's 0.3 in diameter, and tangential velocity, the inlet velocity, so 50 feet per second, that is 15 meter per second. Okay, then what will be the this Fc by Fg? So is around 155. So the separation factor is 155. That means Fc equal to 155 by Fg, right? So the centrifugal force is 155 times stronger than the gravitational force, right? That means the separation will be very easy. The separation is mainly because of the centrifugal force, not because of gravity. So the particles will be easily separated, right? Okay. So also the purpose of using centrifugal settling processes is that in gravity settling, the process is very slow, right? But in centrifugal settling process, the force is very high, very large in magnitude. So the separations becomes very fast. Okay, that is also the main purpose. Okay, so please remember this. This is a separation factor. So what will happen if you choose a cyclone of lower diameter, right? A small cyclone of less than, and you have, let's say you have another cyclone of bigger diameter or bigger radius, right? Capital R and small r. So for a given feed and at constant velocity, which will give you higher separation. Okay. So definitely this will give you, the smaller cyclone with smaller radius will give you the higher separation, higher removal of the particles. Because you can see here, if you put this separation factor is inversely proportional to the radius of the cyclone. So lower the radius of the cyclone, the higher the separation factor. If you have larger radius or diameter of the cyclone, then you will have, lower value of separation factor. So it is easier to separate in smaller cyclones than in the larger cyclones. Okay, but the problem in the smaller cyclones is that you cannot operate on large feeds. Okay, so you cannot separate large feeds from dust particles. But if you use larger cyclones, you can have larger feed size, but the problem is the separation will not be there. It's useless. So the point is, if you want to separate large feeds, then use multiple smaller cyclones. Okay. So there is, so you have also collection efficiency called. So what is collection efficiency? So suppose you put 1 kg of dust particles in the feed and you have collected, let's say, 500 grams. Okay. So what is the collection efficiency? It is simply you have collected 500 divided by 1. So it is point. So 50% collection efficiency, right? Suppose you have put 1 kg of dust particles in the feed and you have collected all the particles. That means collection efficiency is 100%. Okay. So this is the called collection efficiency in percent. Okay. So they have plotted this collection efficiency for 3 categories. Mainly, if you see here, so the diameter is increasing. So the diameter of A cyclone is 14 inch, B is 31 inch, and C is 70 inch. So they are increasing. So if you plot the collection efficiency, what you can see, and there is also diameter. Okay. So on x-axis we have diameter, and on the right vertical axis we have collection efficiency. So definitely, if you increase the diameter, if you use larger particles in the feed, then what will happen? Every particle will get collected at the bottom of the cyclone, right? So for all the 3 cases, irrespective of the diameter, so you will get 100% collection efficiency. But if you have smaller particles, right, small sizes, then which will give you higher collection efficiency? The cyclone with the lower diameter will give you the higher collection. So you can see it. So first see the curve for A with diameter cyclone 14 inch. So for the cyclone A, you can see the collection efficiency increases with the increasing diameter. Similarly, for cyclone B, the collection efficiency increases with diameter. That means heavier particles you have in the feed, more particles will get collected, okay, at the bottom. So, and for similarly for the C, same trend. If you increase the diameter of the particles, then more collection efficiency. But for a given fixed diameter of particle, you can see the cyclone A with the lowest diameter gives you 60% collection efficiency, B gives you 40% collection efficiency, and C gives you around 20% collection efficiency. So the collection efficiency for a fixed particle size will be higher for the lowest diameter or lower diameter cyclone, and it is less for the higher diameter cyclone. Okay. So please remember this. Next, we have hydrocyclones. As I told you, in hydrocyclones, instead of using air, we have liquid and particles mixture. So the principle is same. Okay. The principle is same. The feed will enter at the tangential velocity at the top. Okay. Then the fluid will go in spirally downwards, right? The particles will be at the wall and they will slide down at the bottom. So you will have some, slurry kind of thing. Okay. And at the center, it is vortex finder. So what will happen is the liquids will again come up through this. Okay. So this principle is same. So there you can change the shape of the cyclone. You can make it shorter or you can make it longer. Okay. So based on the shape of the cyclone, the separation criteria of this cyclone will be different. So if you have a longer cyclone, then this cyclone will be in thickening mode, and if you have shorter cyclone, then you will have classifying. You already know what do you mean thickening. Thickening is nothing but clarifying, so you'll completely separate the liquid from the solids. In classifying, you will have a range of fractions of solid particles getting separated, or you will get some kind of differential solid fractions. Okay, so the principle is same as the air cyclone. So also you have centrifugal decanters. Okay, so what is the purpose of centrifugal decanters? Basically, it separates liquid from liquid. Okay, suppose you have a water and kerosene mixture. Okay, the kerosene is lighter than water, so kerosene will float on the water, but you want to separate that. So simply put in the centrifugal decanter, rotate it at high velocity. So the water which have higher density will be collected at the outermost region, and the kerosene will be here at this region, okay, in the lower radius region. So you can easily collect the kerosene from this region and collect water from the outer region. Okay, same. So within this centrifugal, we have two kind of centrifuge. So we have tubular, as the name suggests, the equipment is in the form of tube. Okay, another we have this centrifuge, so it's kind of disc, right? It's not long, it's short, like this. Okay, the principle is same. Okay, if you rotate this mixture at very high velocity, angular velocity, so the heavy liquid will be collected at the outer side and the lighter liquid will be collected at the lower side. Okay, so in tubular centrifuge, the feed is feeded at the bottom. So feed will come here, this liquid mixture, then it will be rotated at very high speed. So the heavy liquid will be collected at the outer region and the lighter liquid will be collected in this lower radius region, inner region. So there we have some kind of notch here. So yeah, this one. So the lighter liquid will get collected and it can be taken out from here, while the heavy liquid can be collected and taken out from this way. Okay. And in case of this centrifuge, the principle is same, only the shape is like this. So feed will come from the top. Okay, then it will get rotated very high velocity. Okay, then what happened, the lighter liquid will be collected at the inner region, so it will get collected through this pipe, and the heavy liquid will be collected at the outer region, so it will collect it from this pipe. Okay, this is rotating at high speed, this is rotating bowl. Okay, and solids will collect it at the outermost region, because solids are heavier than the liquids.